Have you ever stopped to think about what really holds things together? Like the bridges you drive over or those huge pipelines. How do we know they're actually safe?
It's a really good question. And it often comes down to, well, engineers having to carefully break things to understand them.
Right, this idea of destructive testing in welding sounds a bit dramatic.
It can be, but it's incredibly important work.
Now, destructive testing covers a lot, doesn't it? But today, for this deep dive, we're really zeroing in on two key types.
That's right. We're focusing on the numbers, the quantitative tests.
Specifically, tensile strength. How hard can you pull it? And impact toughness. How well does it handle a sudden shock? We got some great material on this.
Yeah, and it's worth clarifying that difference. Quantitative tests give you a measurable property, like strength in, say, newtons per square millimeter or toughness in joules.
Okay.
Then you have qualitative tests, like a bend test, which are more about just seeing if it holds up, if it cracks or not. But today, it's all about those precise quantitative measurements.
Got it. So let's start with strength. When we talk about the overall strength of a welded joint, where do engineers begin?
Usually, the starting point is the transverse tensile test.
Transverse tensile. Okay, what's the goal there?
Well, the main objective is simple. Prove that the whole welded joint, base, metal weld, everything meets the strength requirements set out in the design.
So you want the weld to be at least as strong as the metal it's joining, right?
Exactly. Ideally, you don't want the weld to be the weak spot. Designers count on that.
Makes sense. So how do they actually, do the test? What do the samples look like?
They prepare these special test specimens. They're often shaped sort of like a dog bone, cut right out of the welded piece. Any extra weld sticking up is ground off, nice and smooth, and these specimens represent the full thickness of the joint.
What if it's like really thick steel?
Good point. For very thick materials, yeah, they might actually cut several specimens from different depths through the thickness. Standards like EN 895 cover how that's done. It ensures you test the whole joint.
Okay, so you've got your dog bone specimen. What's next?
It gets measured very precisely. Then it's clamped into the jaws of a tensile testing machine.
Sounds serious.
It is. The machine then applies a pulling force, a tensile force, that increases steadily and continuously.
Just pulling?
And pulling, until the specimen eventually breaks, fractured.
It breaks. How do you get the strength value from that?
It's actually a pretty straightforward calculation. You take the maximum load, the highest force the specimen resisted just before it broke.
Right.
And you divide that force by the original cross-sectional area of the specimen, the area you measured before you started pulling. That gives you the tensile strength, or R.
A clear number. That's the joint's ultimate pulling strength.
Exactly.
What counts as a pass then?
Yeah.
When is the result acceptable?
Well, if the break happens right in the weld metal itself, it's usually acceptable as long as the calculated strength meets or exceeds the minimum required for the base metal.
Okay.
But what's interesting, in codes like ASME IX, which is a big one, if the specimen breaks outside the weld, like in the base metal away from the weld zone, but the stress reached was still over 95% of the base metal's minimum required strength, that's also considered acceptable.
Huh. So failing in the base metal can actually be a good sign for the weld.
In a way, yes. It shows the weld itself was stronger than the material around it, or at least strong enough.
That is interesting. Okay, so that's the joint strength. But sometimes you need to know about just the weld metal, right?
Yeah.
By itself.
Absolutely. That's where all weld tensile tests come in.
Why the need to isolate the weld metal like that?
Several reasons. It's really critical for measuring the weld metal's specific tensile strength, its yield strength. That's the point where it starts to deform permanently.
Right.
Or its proof strength if it doesn't have a sharp yield point. And also its ductility, how much it can stretch. This is vital for designs that operate at high temperatures, for instance.
Okay, elevated temperatures matter.
Definitely. And also, welding consumable manufacturers use these tests all the time to certify their electrodes or wires, ensuring they consistently produce weld metal with specific properties.
So the specimens must look different for these tests.
They do. Instead of cutting across the weld, these are machined from the weld metal, running parallel to the direction the weld was laid down.
Yeah.
The key thing is that the section being measured, the gauge length, is entirely weld metal. Think of it like a small, round bar taken right from the core of the weld deposit.
Gotcha. And the testing method, still pulling.
Still pulling, yes, with that continuously increasing force. But there's a key addition. A device called an extensometer.
Extensometer, what does that do?
It's clamped onto the gauge length, that parallel section of the specimen, and it measures very precisely how much that section stretches as the load goes up.
Ah, so you're measuring stretch directly.
Exactly. This lets you pinpoint the yield strength, or calculate the proof stress, RP, for materials that yield more gradually. If you plot the load versus the extension, you get these characteristic load extension curves.
Like a fingerprint for the material's behavior under load.
That's a great way to put it, yeah.
And you mentioned ductility earlier. These tests measure that too.
They do. Tensile ductility is super important. It tells you how much the material can deform before it finally breaks.
How much give it has.
Right. We measure it mainly in two ways. Percent elongation, how much longer the gauge length got compared to its original length.
Okay.
And percent reduction of area. This looks at the fracture point and measures how much the cross-section narrowed down before it broke.
Is that what they call necking?
That's it, exactly. You see that distinct narrowing, that necking, right where it's about to fail. Higher ductility means more necking, more stretching.
So all these numbers, strength, yield, ductility, they're fundamental for engineers, aren't they? Making sure things don't just, well, fall apart or stretch too much.
Absolutely fundamental. They provide the quantitative proof that the materials will behave as expected under real-world stress.
Okay, so we've covered strength, resisting that steady pull. But what about sudden impacts? Especially, say, in the cold. That feels like a different challenge.
It absolutely is, and that's where we need the Charpy V-notch impact toughness test.
Charpy V-notch. Okay, toughness. What's the goal here?
The objective is all about assessing the material's resistance to brittle fracture.
Brittle fracture, that sounds bad.
It is. It's a sudden, often catastrophic failure with little warning. The Charpy test measures the energy needed to start and grow a crack from a sharp notch when the material is hit suddenly.
And why is this so important for designers?
Because they have to prevent brittle fracture in service. Especially if a component might see impact loads or operate in cold environments, strength isn't enough if the material is brittle.
You mentioned cold. The temperature effect is huge here, isn't it?
Oh, absolutely critical, particularly for common steels like carbon, manganese, or low alloy steels. Their toughness can change dramatically with temperature.
How so?
A steel might be perfectly tough and ductile, meaning it bends before it breaks at room temperature, but take it down to sub-zero temperatures and it can become incredibly brittle, like glass. It might just snap under an impact it would easily absorb when warm.
Wow, so engineers need to know how it behaves at the lowest temperature it might encounter.
Precisely. They identify what's called a transition temperature, a point where the behavior shifts from ductile to brittle. They need to ensure the material stays tough enough, even below its expected minimum service temperature.
Okay, so the specimens for these Charpy tests, are they standard?
Very much so. They have precisely defined dimensions, typically 10 by 10 millimeter square section, 55 millimeters long, with a specific V-shaped notch machined into one face. There are also smaller, sub-size specimens for thinner materials.
And where do they take these specimens from in a weld?
The notch position is critical and specified by standards. Typically, you'll test with the notch located right in the center of the weld metal.
Okay.
But also, crucially, at different locations within the heat-affected zone, the HAZ. That's the base metal right next to the weld that got heated during welding but didn't melt.
Why test the HAZ too?
Because welding changes the properties of the base metal in the HAZ, and sometimes the HAZ can become less tough than either the weld or the original base metal. You need to find the weakest link in terms of toughness.
Right. Makes sense. So walk me through the test itself. It involves hitting the specimen.
It does. The method is quite dynamic. First, the specimens are cooled down to the exact test temperature in a special insulated bath. Could be alcohol and dry ice or liquid nitrogen for very low temps.
Oh, you get it cold.
Then, working quickly to prevent warming, the specimen is placed on the anvil supports of the Charpy testing machine. Then, a heavy pendulum hammer, raised to a standard height, is released. It swings down, strikes the specimen on the face opposite the notch, and breaks it.
And you measure something from that swing.
Yes. The machine measures the energy absorbed by the specimen during fracture. As the hammer breaks the specimen, it loses energy, so it doesn't swing up as high on the other side. The difference tells you how much energy the specimen absorbed.
Measured in?
Usually joules, though you'll see foot-pounds, FT pounds, in some U.S. specifications.
And I read somewhere they test multiple specimens.
That's standard practice, yes. Because toughness results, especially in welds and HAZs, can have some variability or scatter, so you normally test 3 specimens at each required temperature and location.
And then you average the results.
Exactly. The acceptance criteria usually involve calculating the average energy absorbed from the 3 tests and comparing that average to the minimum value specified in the code or design standard. Sometimes there are rules about minimum individual values, too.
Okay. Now, you mentioned looking at the broken pieces afterward gives you more info.
Yes, there's valuable additional information you can get visually. One key thing is the appearance of the fracture surface specifically, the percent crystallinity.
Crystallinity.
Yeah, a brittle fracture surface looks bright, granular, crystalline. A ductile fracture looks duller, more fibrous. So by estimating the percentage of the fracture face that looks crystalline, you get a measure of how brittle the failure was. 100% crystalline means a completely brittle snap.
Interesting. What else?
The other important measure is lateral expansion. After the specimen breaks, you measure how much the sides of the specimen, just behind the notch root, have bulged outwards due to the plastic deformation during impact.
So more bulging means?
More bulging, a higher lateral expansion value, means the material was tougher. It deformed more before and during fracture, absorbing more energy.
So you can really see the difference between brittle and tough failures.
Oh, definitely. A very brittle specimen breaks cleanly, often in 2 halves, with a flat, shiny fracture face and almost no lateral expansion.
Just snaps.
Right. Whereas a very tough specimen might not even break completely through. It might just crack part way, show a lot of tearing, a dull fracture surface, and significant lateral expansion, indicating it absorbed a lot of energy.
That's a stark contrast. It really highlights why this toughness testing is so vital for preventing those sudden, scary failures.
Absolutely. It's about ensuring resilience against unexpected shocks or cold conditions.
So, stepping back to see the bigger picture, we have tensile tests for strength and Charpy tests for roughness. How do they work together?
They're complementary, really. Both are crucial quantitative destructive tests, but they measure different essential properties. Tensile strength tells you the material can withstand the expected steady loads without pulling apart.
Okay, handles the planned forces.
Right. Impact toughness, specifically Charpy testing, assures you it won't suddenly shatter like glass if it gets hit unexpectedly or the temperature drops significantly. It addresses resistance to brittle fracture initiation and propagation.
So one protects against yielding or breaking under tension, the other against shattering under impact.
You've got it. They cover different failure modes, both of which could be critical depending on the application.
Let's try and summarize the core insights then. What are the key takeaways for someone listening?
Okay. Tensile tests are fundamentally about measuring the force needed to break a joint, or the weld metal itself. They give you key metrics like ultimate tensile strength, yield or proof strength, and ductility, how much it stretches.
Strength and stretch, basically.
In essence, yes. And Charpy tests are all about assessing a material's resistance to brittle fracture, especially how that resistance changes with temperature. They give you impact energy values, telling you about its resilience to sudden shocks.
Resistance to shattering, especially when cold.
Precisely.
And these aren't just theoretical exercises, are they?
Not at all. It's vital to remember these tests are fundamental tools for welding procedure qualification. Before major fabrication work starts building a bridge, a pipeline, a pressure vessel, these tests are done on trial welds.
To prove the welding method works.
Exactly. To prove that the specific combination of materials, welding process, and parameters produces joints that meet the safety factors and design requirements laid out in engineering codes and standards, they provide the objective evidence needed.
So from the steel plates in buildings to the pipes carrying gas, these tests are the unseen guarantee of safety and performance.
That's a perfect way to put it. They underpin the reliability of so much of our modern infrastructure.
We've definitely gone deep today into tensile strength and Charpy impact toughness, 2 really critical pieces of the destructive testing puzzle. Hopefully, you've picked up some useful insights into how engineers make sure the materials around us are strong and safe.
Yeah, it's quite the process, and maybe it leaves you with something to think about. Now that you know a bit more about how meticulously materials are tested for both strength and toughness, does that change how you look at, that bridge you cross or even just the frame of your car, knowing the engineering rigor that goes into ensuring they won't fail unexpectedly?
That's a great thought to end on, something for you all to consider. Join us next time for another deep dive where we'll pull apart another fascinating topic.